Hey, today I'm gonna talk about the centripetal acceleration. I'm gonna show you guys the proof, okay? And in uniform circular motion. So what is uniform circular motion? First of all, it's a 2D motion. It's not 3D. So let's just say you're going from left to right and front to back. That's it. You don't go up and down. This is just 2D. Okay, in this case, in here, we're just going to the left. We go to the right. We go to the left. We go up and we go down. So that's it. It's just 2D in here. Okay, on the plane. So it's circular because it's circular. Okay, this R1 here is the position vector. It's like you got a car on the road. The car is here, and then it comes over, and then it comes and comes and comes and comes and comes. And the car just keeps coming and coming, and when it gets to this point, it goes again, okay? And it goes again. Now, it's very important. Uniform circular motion, that means that it's circular because it's circular. This R1 has the same magnitude as the R2. I'm going to explain these terms in time. And it's uniform because the linear velocity, which is the V1 here, has the same magnitude as V2 over here. Okay, you cannot have a V1 that's larger like this, and you cannot have a V1 that's smaller like this. So it has to be the same size as V2. I did all these manually, so that's why they came out like this. Anyway, since it's circular, R1 is always going to have the same magnitude as R2. Now, what is R1 and R2? These are the position vectors, okay? Now, you got to remember, a vector is something like this, okay? So it has a magnitude, which is the length of this, is the size, and it has a direction, so it's going this way. You can have a vector of kind of the same size, like that, okay? So it kind of has the same size, not perfectly because I'm not a robot, maybe a little bit longer. So this one here and this one here have the same size, but this one has a different direction. It's going this way, and this one is going this way. So these two vectors are different. So in order for two vectors to be equal, they have to have the same size, the same magnitude, okay? Magnitude is the size, the length. And it has to have, they gotta have the same direction. They gotta have the same direction. Okay. So knowing this, the notation for a vector, in this case, for example, R1, I'm just gonna write it like this, R1, and then you have a little horizontal arrow here, just indicate that this is a vector. So what would be the format of this? It would be something like this, like maybe R cosine of t, t is the time in seconds, for example, plus R sine of t, okay? So this R here would be the magnitude, would be the scalar, which represents the length of this R1 and obviously the length of this R2 and any other length in here, because it's circular motion, the radius cannot change, okay? Now, what is V1? V1 is the velocity vector. Now you got to remember, what is velocity? In calculus, velocity is the derivative of the space with respect to time. So in here, it's the derivative of the position vector R1 with respect to time. So if you do dR1 dt, you're going to have V1. Okay, you're going to have the velocity vector 1. Now, let's try to get the derivative of this. What would it be with respect to time? It's going to be minus R sine of t, okay, plus R cosine of t. So this right here is going to be the velocity vector. So this is R1, so this is V1, okay? And the derivative of the velocity vector is going to be the acceleration vector. So A1, the vector A1 is going to be the derivative of this one with respect to time, right? So what is it going to be? It's going to be minus R cosine of t minus r sine of t. This is going to be the vector a1. Okay, so you don't actually have to memorize all these things. I'm just showing you this to get you in the context, to give you some kind of background knowledge, because we're going to need this. Oops, hold on. I gotta change this color here, otherwise it just doesn't work. I'm erasing these things. Okay, so here we go. At some point in time, the car is over here, okay, and then the car is gonna be over here. So this is the position vector r1 on this yellow path where the car is going around and around and around. And this is going to be the second position vector at some time t later, okay? So this is the position of the car first, and then this is the position right here. Okay. Now, what is the centripetal acceleration? Why in a uniform circular motion you can only have centripetal acceleration? Which is, what kind of acceleration is that? Is the acceleration that changes only the direction of the velocity vector. It cannot change its magnitude, okay? Because if it changes its magnitude, that means that the speed of the car is going to slow down. Oh yeah, there's something else that I have to explain to you. Velocity is, for example, this v1 here is the velocity. It's a vector. Okay, it has magnitude and it has a direction. The speed is the magnitude of the velocity. So speed is just the magnitude of the velocity. It will be the absolute value of the magnitude of the velocity. So speed is a scalar and the velocity is actually a vector that has a magnitude and a direction. Okay, now where was I? Okay, so the car is here and then it comes over here at some time t later. Okay, you can see one thing here. First, this is the position vector r1 when the car is here. This is the position vector r2 when the car is over here. Okay, now the centripetal acceleration, which is what we're trying to find out here. What direction is the centripetal acceleration? It always has to be at a right angle to the velocity vector. It cannot be, for example, the centripetal acceleration, the vector, which represents the centripetal acceleration, cannot be like this. Why? Because in here you can break this vector right here into two. Okay, one coming along v2 this way, and one over here this way. If you sum these two vectors, you're going to get this one. Now, what is the problem with having an acceleration vector going along v2? That means that v2 is going to increase. It's going to be larger than v1. And the magnitude of the vector, the velocity vector, can never change. Otherwise, it's not uniform circular motion. You want uniform. The length, the magnitude, the speed can never change. If the car is going around here, okay, at 55 miles per hour, it's going to remain at 55 miles per hour. It's just the direction of the velocity vector that's going to change over time. But the car is always going to be at 55 miles an hour. It cannot be at 56. It cannot be at 54. Otherwise, it's not uniform circular motion anymore. Okay? So, all right. So let me get back to this centripetal acceleration here. So when the car is over here, okay, and at this point, this is the velocity vector, because it's the velocity vector. This is the linear velocity, so it's always tangent to the path. Okay, so when the car is at this point, the velocity vector is here. When the car is at this point, the velocity vector is here. The centripetal, how do I explain this? Yeah, centripetal acceleration vector is always going to be on top of the positional vector. But the length, the magnitude of the centripetal acceleration vector may change, and it's going to be on the opposite sign of this R1. So you see, I'm going to make it like in green here, and I'm going to make it thicker. Okay, Hold on. I know this is kind of complicated, but it is complicated. So, okay. At this point, the centripetal acceleration is going to be something like this. I'm going to put right on top of it. It'll be something like that. Okay? Let me make it straight. It'll be kind of like this. It'll be right on top of it. It may be this long. It may be this long right here. It may be this long. Okay? But it's always going to be to the inside of the circle. Like that. Okay? This is going to be, for example, it's just an example, the centripetal vector in here. Over here, the centripetal acceleration vector is going to be like this. All right? Now, you see, okay, so this is the centripetal acceleration here. This is the centripetal acceleration here. Now, this is very important. The magnitude, the length of the centripetal acceleration vector cannot change either. Because if it changes for the less, okay, let's just say that it gets smaller, then the car is just gonna drift away. It's gonna start in a circle like this, and then slowly it'll just drift away. All right, and you don't want that. Now, if the centripetal acceleration vector gets larger, the car is gonna start, okay, in a keep going, but then at some point it's just gonna keep going inside and inside and inside in a swirl. I don't think there's a swirl. I think it's some kind of curl. I don't know, something. Right? So it'll go inside like that. If the centripetal acceleration is too large, the centripetal acceleration has to be just right for the car to have circular motion. It's always going to be on this yellow path. Okay, always going to be on the yellow path. All right. Now, let me change here. Put like that. No. Maybe a little bit. Oh, yeah, that's fine. Yeah, that's fine. Okay. So, here you got a centripetal acceleration, yeah, and the centripetal acceleration vector always has to be perpendicular to the velocity vector. Why? Okay, I already explained this before, otherwise it's not going to be uniform. So the centripetal acceleration vector has to be this at this point, and it has to be this at this point, okay? Now, this is getting kind of clogged in here. So let's just say the car is over here at this point. At this point, the positional vector is going to be this one. This is going to be, for example, R3. The velocity vector has to be the same length of this. So it has to be kind of like that. Okay, maybe a little bit larger. This is going to be V3. And the acceleration vector, I have to put it exactly on top of R3. And it has to come this way. This is the part that I want to erase R3 from here, so it's not going to get too clogged. Okay, the centripetal acceleration is going to be like this. Hold on, at this point, like this, kind of like that. This is going to be A3. Okay, so it has to be always perpendicular and going to the inside of the circle. Always perpendicular to what? Perpendicular to the velocity vector at that point. Okay. All right, now what do we have to get from here? I made a triangle here, two triangles as a matter of fact. First, just worry about the white part of this large triangle, okay? R1, I copied it over here. This position vector here is the same one as this position vector here, okay? I just copied this thing from here to here, okay? So R2 is over here, all right? Now, what is the difference between R1, R2, and R1? R2 minus R1 is going to be this vector right here, this vector, okay? Now, what do we learn from physics, like at the beginning of mechanics, okay? That the difference of the space over time equals the average velocity. This is not a velocity vector. All these are scalars, okay? And the difference of velocity over time equals the average acceleration, okay? So let me get this here. Okay, so what do we have here? You see, R2 minus R1 is going to be delta R. Okay? Now, what you can see is that the triangle, you see, R1 is one of the sides of a triangle, R2 is the other side of the triangle, and R2 minus R1 is the third side of the triangle. Now, you can see that as much R1 changes into R2, this angle right here, let's call it theta, okay? V1 is also going to change into V2 by the same amount of, by the same angle, theta. How do I know that? Because V1 is perpendicular to R1. So V1 equals R1 plus 90 degrees. See the 90 degrees here? Okay. And V2, the angle of V2 is just going to be the angle of R2 plus 90 degrees. You can see the 90 degrees here. Okay, so if R1 changes into R2 by this amount, the theta angle, V1 is going to change into V2 by the same theta angle. There's something else too. Because this is uniform circular motion, the size of R1, this length right here, has to be always the same size of R2. It cannot be longer or shorter. Okay, the same goes for, because it's a circular motion. Because it's a uniform motion, the length of V1 has to be the same length of V2. Okay, what am I trying to get with this? I want to go with this to the point that how can I put this into words for you guys to understand? V1, I'm talking about the length, okay? So the length in vector, this is how you do it. This is the notation of vector, and then you put a double bar here and a double bar here. So this is the magnitude of V1. This is a scalar now. This scalar divided by the scalar of V1, well, okay, V1, okay, the scalar of V1 divided by the scalar of R1 is going to be equal to the scalar of V2 divided by the scalar of R2. So the magnitude of V1 divided by the magnitude of R1 equals the magnitude of V2 divided by the magnitude of R2. Why? Because these two right here have to be equal, right? If they were not equal, the motion would not be uniform. And these two right here have to be equal. If they were not equal, the motion would not be circular. All right. So that's one thing right there. It's because it's a lot of concepts, guys. It's complicated. Okay. I mean, for people that already know this stuff, it's second nature, second-hand nature. But for people that are trying to understand this for the first time, this is complicated and the books don't make it clear. Okay, now you can see that as much as R1 is going to change into R2 by a difference of by an angle difference, V1 is going to change into V2 also by an angle difference. And this size divided by this size equals this size divided by this size. Where am I going with this? I'm saying that the fraction that V1 is of R1 is the same fraction that V2 is of R2. And the angles are the same. The change in the angle is the same. Okay, so look at this. This is the angle theta. Okay, the same angle right here is over here. So why is this important? Because R1, R2, and R2 minus R1 are three vectors that form a triangle. Now, V1, V2, and V2 minus V1 are three vectors that form another triangle. And these triangles have V1 and V2 are the same size, and R1 and R2 are also the same size. And there's something else too. The change in angle is the same, okay? As much as R1 changes into R2, V1 changes into V2. That makes these two triangles similar. So you got a large triangle here. This is all a big triangle. It's similar to this smaller triangle here. Why is that important? Because here we go now. You got to remember all these concepts to understand how to calculate the centripetal or the centripetal acceleration. Okay, how do you calculate how much it is? According to the magnitude of the radius and according to the magnitude of the linear velocity, how do you know how to calculate the length of this centripetal acceleration here, and the length here, and the length here? Okay, these lengths all have to be the same. The arrows are just different size here because I'm not a robot. I'm not going to make them perfect. But they all have the same length, okay? This one is as large as this one, is as large as this one. But there's a value here. Is the value here 3? Is the value 7? Is the value 15.8? Which one is the value? How do I find the value, okay? That's what this whole video is about. Okay, so what you gotta do is to know that since these two triangles are similar, R1 minus R2 divided by R1, for example, is going to be similar. It's going to be the same thing as V2 minus V1 divided by V1. Okay, so this length divided by this length equals, okay, pay attention to this. This length divided by this length equals this length divided by this length because they're similar. So let's do that. Okay, this is delta R and this thing here is delta V. Okay, so let's do this. You have delta V. Okay, and this I'm talking about the magnitude, so it's like that, divided by the magnitude of V1. It's the same as the magnitude of V2, but I'm just going to pick up V1 to make it simpler. Well, I'm not going to pick V1 or V2. Why? Because since we're talking about magnitude, the magnitude of V1 is the same as V2, so it's the same as every V. So I'm just going to divide by the magnitude of V. It doesn't matter if it's V1, V2, V3, V4, V5. They're all the same size. Now, is delta V always the same size? No, because you see, delta V is, for example, let me just write here again, V1, okay, and at some point later, V2 here. This V2 is too large. I'm gonna make it kind of the same size. Okay, so V2. So what is the difference between V2 and V1? The difference is this, right? This is the difference. Now let's do V1 here again. This is V1, and like a millisecond later, I measure it again, and right now V2 is over here. So what is the difference between V1 and V2 now? This is V2. What's the difference between V1 and V2? It's just this. This is V1 minus V2. Can you see that this one here is a lot larger than this? Okay, so the change in the velocity vector, the change in the position vector are not going to be the same according to time. They're going to change over time. Now, the length of the radius of R1 is always going to be the length of R2, which is going to be the length of R3 here, which is going to be the length of R4. This length doesn't change. That's why it's circular. And the length of V1 and V2 also don't change because it's a uniform motion, uniform circular motion. So I'm just going to pick V here. It doesn't matter. So delta V divided by V, meaning this length divided by this length, okay? The magnitude of delta V divided by the magnitude of V okay, equals, because the triangles are similar, is going to be the magnitude of delta r, okay, over the magnitude of r. Which r? This r or this one? It doesn't matter, because it's circular motion. That means that the magnitude of all r's are going to be the same, and the magnitude of all v's are going to be the same. Okay, that's why this is just v and this is just r. Doesn't matter. Now, what am I going to do? I'm trying to find out the magnitude of the centripetal acceleration. I'm trying to find out the magnitude of the centripetal acceleration vector. Okay, so what am I going to do? Well, I know that the derivative of the velocity vector, okay, because this is just an average change in the velocity vector, okay? It's this v2 minus this v1. Now let's just say that I take the derivative. What's the derivative? Okay, the derivative, if you guys don't remember calculus, that will be the limit of delta v, the vector of delta v, divided by delta t as delta t approaches 0. All right, so the derivative of the velocity vector with respect to time is going to be equals to the instantaneous acceleration vector, and that's what I'm trying to find out. This is the centripetal acceleration vector that I want. Okay, so what am I going to do? I'm going to isolate this thing right here. Okay, I'm going to put this stuff over here. So what am I going to do? I'm just going to, I don't know if this is going to work out. I hope it does. Just going to bring this stuff over here. Okay? Here you go. Okay. Now, you don't have to worry about this thing here. Okay, that's fine. Now, what am I going to do? I have here a change in velocity. Well, if you differentiate the change in velocity with respect to time, what you're going to get, okay, is the instantaneous centripetal acceleration vector. So that's what I'm going to do. I'm going to get this delta v here. I'm going to differentiate it with respect to time. That's going to give me the centripetal acceleration vector, and for me to find the scalar of the centripetal acceleration vector, I'm going to find the magnitude of it. Okay, so first I differentiate and then I find the magnitude of it. Now, okay, so I'm just going to do all this stuff here in one step, two steps to make it even easier. So what is the derivative of the change in velocity vector with respect to time? It's going to be the acceleration vector, okay? And then I'm going to take the scalar of it, the magnitude of it. Now, if I differentiated this side with respect to time, I got to differentiate this side with respect to time. Now, here we go. Let's talk about this v right here first, okay? This v, is the length of this v going to change with respect to time? No. What did I say? That this length of this v has to be the same length of this v. When the car's over here, it's going to be the same length of the v3 here. When the car's over here, it's going to have the same length of the v4 here. So the length of the velocity vector is not going to change with respect to time. It's just a constant. So with respect to time, this v is a constant. That's what makes it uniform motion. Now, same thing goes for r. Does the radius increase or decrease with respect to time? No, the radius stays the same. So as you differentiate this whole thing, this term and this term are constants. If they're constants, all you got to do is repeat it. Okay, so you're going to have the magnitude of the velocity vector divided by the magnitude of the radius vector. Okay. And now, here comes the magic. Is the delta r, the change in the position vector, going to change with respect to time? Yes, it will. See, over here, back over here, R2 minus R1 is going to be this size. Look at the size of this. Okay, that's the size right here. This is the size of the thing. Now, let's just say that a little bit after a small, very small time after it's in R2, I measure the thing again. What are we going to have? We're going to have another position vector here, kind of like this, which is going to be R3. Okay? Now, what is the difference between R3 and R2? You can see that the difference between R3 and R2, R3 minus R2 is going to be just this. It's a very small vector. Like I said before, okay? It depends on when you measure. If you measure a long time later, the vector is going to be larger. The difference vector is going to be larger. If you measure a small time later, the difference vector is going to be small. So this is going to change right here with respect to time, this term. Now, what is the derivative of the difference in position vector with respect to time? Well, you're differentiating position with respect to time. That's velocity, okay? So if you have a vector here, this is the position vector, you differentiate it with respect to time, what are you going to get? You're going to get the instantaneous velocity vector. So that's what I'm going to do. I differentiated this side with respect to time and I got acceleration. Differentiating this side with respect to time, you're going to get the velocity vector. But I'm working with magnitude in here. So I'm going to calculate the magnitude of the velocity vector. Okay? Now, get this. You got a velocity here and you got a velocity here. Can this, the magnitude, not the vector velocity, but the magnitude of the vector velocity, can it change with respect to time? No, the magnitude cannot change. Remember, the magnitude of the velocity vector is the speed. The speed can never change. That's why it's a uniform motion. So this magnitude right here equals this magnitude right here. They're the same magnitude. What am I trying to say? If this is 4, this has to be 4. Okay? So what is this? You got a magnitude times a magnitude. That means it's the magnitude squared. Okay? So I'm just going to erase this thing here because this video is already getting way too long. And I'm going to put a 2 here because it's squared. And there you go. The magnitude of the centripetal acceleration equals the square of the magnitude of the linear velocity divided by the magnitude of the position vector. Now, if you're just, all these are scalars, okay? So in order to try to make it simpler, what if I say, if I say that a car is going at a linear speed of 8 miles per hour, okay? And well, let's just 8 miles per hour, and the velocity vector is just the position vector has a magnitude of 3. Okay, this is the radius. So the radius, let's just put miles too, because if it's miles in here, it's got to be miles in here. So what is the acceleration? The acceleration here. Okay, now this is a scalar, this is not a velocity, this is a scalar. The acceleration is going to be the square of the velocity vector, which is 64, divided by the radius vector, which is 3. So it's just this, okay? I think because you're using miles an hour here, it's going to be the acceleration miles per hour squared, okay? And that's it. That's how you calculate the centripetal acceleration. The formula, just to make it easier, the formula when you just care about the scalars, you don't care about all this vector stuff, is just to prove the scalar formula, okay? But really, what's important, what you gotta take from this video, what you gotta learn from this video is that centripetal acceleration, we put a little c here, a subscript c alongside the a. So centripetal acceleration equals the linear velocity squared divided by the radius in uniform circular motion. And that's it.